So thank you very much. So today I'll talk about Annulus-like global surface of section and this fixed point theorem by Poincaré and Birkhoff. So okay. Okay, so let me say something about the story of this problem. In 1912, Poincaré published that paper there, and he studied the circular planar restricted three-body problem, and he shows the existence of infinitely many periodic orbits there. Okay, and for that, he uses this Annulus-like global surface of section. He constructs this global surface of sections, and he observes that the first return map associated to this global surface of section has some very nice properties, and then that's how he obtains these infinitely many periodic orbits of this first return map using this type of reduction, okay? So in this talk, I will try to explain the construction of Poincaré, how you obtain this global surface of section, and discuss about the proof of the Poincaré-Birkhoff theorem in a special case, okay? So the Poincaré-Birkhoff theorem, in fact, it's a theorem of Birkhoff, because Poincaré didn't prove it in this more general situation. States that if you have a homeomorphism of the annulus, which is homotopic to the identity, meaning that it preserves the boundary components and preserves orientation, and suppose that also it preserves area and twists the boundary of the annulus in opposite directions. I will explain later what that means. It's, in fact, this is what is called the twist condition. Then this map must have at least two fixed points. And then a direct corollary of this theorem is that the map, this homeomorphism, must have infinitely many periodic points. Okay, it's an application of the previous statement for iterates of the map psi. So the idea is the following. So what does it mean, twist the boundary? So you have a map of the annulus, okay? So you lift this map to the strip, which is R cross the interval 0, 1, okay? And the twist conditions means that if you look at the points in the upper boundary and the lower boundary, they move with different average speed, okay? It's possible to associate to each boundary component of the strip a rotation number, a real number, which measures this speed, how much, what's the average speed in the horizontal direction. And if these rotation numbers are different, then we say that there is a twist condition. In general, the twist condition for us will be that the rotation number, let's say, in the upper boundary component is positive, so the points move to the right, and in the lower component, it's negative, meaning that the points move to the left, okay? And then what is possible to prove is that for that lift, that particular lift, it must have at least two fixed points, okay? And then you can iterate the lift and shift in the horizontal direction by an integer, so that for each rational number in between the interval determined by the rotation numbers on the boundary, you produce a lift of an iterate of psi, which satisfies the twist condition, and so it must have at least two fixed points, applying the theorem. And again, this fixed point corresponds to a periodic point of the original map. So you can do it for any rational number in that interval, and this is how you can show the existence of infinitely many periodic points of the Annulus map, okay? So let's see how Poincaré obtained infinitely many periodic orbits in the circular planar restricted three-body problem. So just, I will recall what many things that were talked before by Urs and Humberto. So let me just recall Newton's gravitational laws. We have three bodies which are point masses, M1, M2, M3, with position R1, R2, and R3. Supposedly they are on R3, but we could even consider on Rn. And later we will consider only on R2, on the plane. And they attract each other by these forces there. And these forces are, they are proportional to the inverse of the distance between the bodies, the square. And we have the Newton's law, which says that mass times the acceleration of the body is the resulting force in that body, and which gives a set of equations describing the motions of the three bodies, these three equations here. Okay, and then I put here in red M3, because we take M3 going to 0. Okay, so we will study the motion of the third body, which is called the satellite, where the first two bodies, M1 and M2, will be given. So we try to reduce the degree of freedom of the system here to 2. So to obtain a system that you can really study. So in this case, when we make M3 equal to 0, we see that the first two equations, they get the form of the two-body problem. M3 does not influence these two first bodies here, so they behave as in the two-body problem. And here in the third equation, M3, you see that it's possible to cancel. So it disappears, this M3. So we still obtain an equation for the third body, even if you were assuming that its mass is equal to 0, okay? So here, these two first equations, they determine the motion of the two first bodies. And you have to see the motion of the third body satisfying this equation here with an input of R1 and R2 given as a solution of this independent system here. So it's a time-dependent differential equation to study the motion of the third body when its mass is equal to 0. Okay? So this will be called the restricted three-body problem. So in the end, the situation that we have, we can normalize so that the sum of the masses M1 and M2 is equal to 1. So M1 we just call mu, which is a parameter of the system. This parameter we cannot eliminate of the system. And then M2 is equal to 1 minus mu, and M3 is equal to 0. Our system has this parameter mu. So we assume in this previous system here that these two bodies, M1 and M2, they are rotating on circular trajectories about their center of mass. Okay, the trajectory is just a circle. Okay, so it's given. So we have in this equation this solution, which are circular trajectories, and they are used to input here these solutions to study the motion of the satellite. Okay. So these circular trajectories, they determine a plane, and M3 is supposed to move on the same plane. Okay, so if you have an initial condition in the same plane, so it remains there. So in the end, we study the motion of the satellite on the same plane. It's a 2 degrees of freedom Hamiltonian system. And but we still have a problem because this is a time-dependent Hamiltonian system, and it's possible to eliminate the dependence on time. How? We just take a system of coordinates. Let's say we have the two bodies rotating, and we put the origin of our system above one of these primaries, for instance, and it rotates with the same angular velocity as these two bodies are rotating. Okay? So we use a rotating system which moves together with the M1 and M2 in such a way that with respect to this rotating system, M1 and M2 stay at rest, and then we look at the equations of motion of M3 with respect to this rotating system. And now, it's very interesting because it does not depend on time anymore. Okay? So it's a time-independent Hamiltonian system, which depends on that parameter, which is the mass ratio between M1 and M2. And it's given in this form here, this expression here. Okay, so this is, in general, the definition of this Hamiltonian is divided by 2, but for some reasons it's better to follow this definition of the Hamiltonian. It doesn't change anything if you divide it by 2, it just parameterizes the solutions. This one is twice as fast as the previous one, so we can make this change. So this Hamiltonian has this form. It has the kinetic part here. It has this magnetic term that we see here due to the rotating system. It's sometimes called the Korolev force that combines position Q on the plane, so and momentum P. So here we use the complex notation, meaning that Q is an element of the complex plane minus these two complex numbers here, because this is where the primaries are located. The heavy primary, I will call the heavy primary because mu will be taken small. It's located at 0. And the other primary with the small mass is located at 1. And this term here, the final term, corresponds to the potential produced by the primaries. Okay? So if you want to study the motion of the third body, we just have to integrate the Hamilton's equations associated to this Hamiltonian system. Okay, but this is extremely difficult, okay, even to find one single periodic orbit. Of course, you have some equilibrium points which are not so difficult to find, some solutions, but to find periodic orbits it's something hard, even for a Hamiltonian of this type. This is essentially due to this term here that you see. Okay, so so the case that I will consider is the case where this Hamiltonian function takes a low value. So this is, I call this the total energy of the system. It's preserved by the flow. So the energy levels, which are three-dimensional in in this case, the phase space has 4 dimensions, the energy level has 3 dimensions. They are preserved. And we study the flow on a component of the energy level for low values of energy. So we don't go above a critical value, okay? So there are some critical values of this function here, but we always stay below the critical value. And we will study the flow restricted to some special components of this energy level. So I was going to draw a picture of the Hills region of the typical energy level. The projection of the energy level to the Q1, Q2 plane. So it's very simple. We have the primary is at 0 and 1, let's say. And if you fix the energy and project to this plane, this complex plane, the Q direction, then it has, typically, for low energy, it has 3 components. One component near, let's say, the heavy primary at 0, which means the trajectories which stay trapped in that region around the primary. There is another component near the other primary, the light primary, correspond to trajectories which stay close to that primary, and also an unbounded component, like a neighborhood of infinity, which corresponds to trajectories which stay very far away, that we don't care about them. Okay, so in the end, we study only the flow. That's what I'm talking about today. That's what Poincaré did in that paper. He studied the flow in this component which projects near the heavy primary. You can imagine like a puncture disk, the projection. The puncture is exactly at 0, which is where the primary stays at rest. And we have a Hamiltonian flow there. It's not complete, but it's possible to regularize. And Poincaré so studied that component of the energy level, the flow there. And that's where he found this Annulus-like global surface of section. Okay, so in order to give a description of the construction studied by Poincaré, in fact, Poincaré studied a perturbation of the case mu equal to 0, equal to 0. So because it is much easier to study this case, which is called the rotating Kepler problem. If we take the previous Hamiltonian and make mu equal to 0, then we obtain this Hamiltonian here. And now, this Hamiltonian is much simpler to study than the previous one. So, first of all, this Hamiltonian has a lot of integrals of motion, but it has independent integrals of motion, which are the angular momentum, given by this term here. Okay. And the total energy in the inertial frame. So if you don't consider the rotating system, the trajectory has an energy with respect to this frame which does not rotate, and this is also preserved by the flow. Okay? This is given by these terms here. So okay. So then, so this system is integrable. It's quite simple to study integrable systems, but in some case, of course, we need to change coordinates in order to clarify the objects that we are studying. So we keep, in this case here, there is a critical level, which is this number here, -3/2. And we keep studying the energy level below this critical value, and the energy level below the critical value has two components. It's a bit different from the three-body problem, where you have these three components. When you project, it's one of them near the light primary, since mu equal to 0, that component near the light primary disappears. It remains only the bounded component near the heavy primary, which is now the projection of that component is a punctured disk. The boundary is really a circle. And there is this unbounded component that we don't consider. We only consider the part of the energy level which is projecting near, like studying if the three-body problem corresponds to the, like say the heavy primary is the Earth, the light primary is the Moon, and the satellite, you have the satellites, the third body. Then we study like trajectories near the Earth. And okay, but there is a problem here when we study this Hamiltonian here. The problem is typical for this type of system. There are orbits which collide with the primary in finite time, so trajectories cannot be continued. In fact, this component of the energy level is unbounded. The projection is bounded, but the energy level itself is unbounded. So it's necessary to regularize the trajectories in order to compactify the energy level and use tools that you can extract information. Tools from, let's say, in that case, from dynamical systems. And okay, I think that it was said before here, this type of regularization, the Levi-Civita regularization. We have Q and P coordinates in the previous Hamiltonian, and we change coordinates to V and U. Okay? So with these formulas here, which are like magic formulas, because it takes that unbounded component which projects into a punctured disk near the primary into a compact energy level. But it's a 2-to-1 map. For instance, if you see that if you, instead of taking V and U, you take minus V and minus U, it will go to the same point, Q and P. So in this regularization, we have this antipodal symmetry, and they will correspond to the same point in the original system with coordinates Q and P. Okay? So, but it's a very nice regularization. Again, first, because it's also symplectic, so the Hamiltonian behaves well under this transformation. And that bounded component, the projection, that projected component, which is the punctured disk, it now becomes an embedded three-sphere. Okay? An embedded three-sphere with a regular flow, and so now we can try to find the global surface of section for this flow on the three-sphere, on this embedded three-sphere. Okay? So there is another part of the regularization, which is you take the original Hamiltonian and then you subtract the energy that we're going to consider. I'm calling this C. C is will be now a new parameter of the system. Okay, so this can be done also in the three-body problem, but I'm considering the Levi-Civita regularization only in this case mu equal to 0, but it works perfectly in the three-body problem. And we multiply the Hamiltonian because this will eliminate the singularities of the previous Hamiltonian here. For instance, p squared here, when you change coordinates, since p is equal to u over v bar, then you gain this norm of v in the denominator, and this will be eliminated by multiplying the Hamiltonian by this function here, but this is not a problem. It doesn't change the trajectories, it just reparameterize the solutions. So it avoids those trajectories which go to infinity in finite time, and it regularizes it. And the new Hamiltonian, after you do all this procedure, takes this simple form here. Okay? This is the new Hamiltonian, which is norm of u squared. You can see this as the kinetic part. V squared, it's part of the potential, but h squared here is a term which combines both variables, u and v, and again, it corresponds to that magnetic term now. We cannot eliminate that this term, but this, again, this is an integral of motion. So this Hamiltonian is preserved by the flow. This is a symplectic transformation up to some factor, and this is a first integral of the flow. Okay. So in the end, after we do the Levi-Civita regularization, our flow is given by these two equations in complex notation here. Okay. So it's integrable, but again, it's not so easy to compute things because it still has some, it's not so difficult, but it's not so easy to visualize the whole flow with these equations in this way. So I will follow with some other change of coordinates to make the system much simpler. Okay, so in fact, I will follow a change of coordinates that I found in McGee's thesis, and then we will see in these new coordinates this Annulus-like global surface of section. So how we do this? So now we are in coordinates u and v. It's integrable, this system. And now we make what is called the diagonalization of these coordinates. We define these new coordinates, xi1 hat, xi2 hat, which has this form here. There is this wave here, the h, which is crucial. And this change of coordinates is not symplectic anymore. So it's not, we cannot just take the Hamiltonian in these new coordinates to study the flow. But we can simply look at the differential equation. We have the equations here in these coordinates. We can, even if this change of coordinates is not symplectic, we can still study the previous system, looking what happens with the differential equation, even if it's not symplectic. And sometimes it's a good idea to do this change of coordinates which are not symplectic because it may give a lot of information of the flow, even if some structure is not being preserved. So now we have, instead of a new Hamiltonian, which is not so important anymore, but we have this flow here in these coordinates xi1 hat, xi2 hat. Okay? And so we have these two equations. So xi1 hat, you can see like a complex plane, xi2 hat, another complex plane. And what these equations are telling us is that the trajectories in both planes that we see, they are contained on circles. So this derivative with respect to time, this new is just a rotation by 90 degrees of the position, because this is a real number here. Okay, there is a factor here. So it's just it gives a rotation. In each factor, we're going to see a rotation, and the flow corresponds to rotation. The only problem of these coordinates is that this rotation is not uniform. Like these terms here, this h here, I said that it's an integral of motion. But q might not be constant. Q is the original coordinate. This might not be constant. So we would see the trajectories like rotating on circles in each complex plane, but they might rotate with different velocities. The velocity is changing, I mean, along the trajectory. Okay? But one of the advantages of these coordinates is that if we look at the energy level, that I said it's diffeomorphic to the three-sphere, in these coordinates here, they become really a three-sphere with this square root of 2 radius. It's really the three-sphere. And the flow is like rotating each factor. Maybe it's not constant here, but it's much better to visualize the flow. And now there is a third change of coordinates. Okay, I found this in the thesis of McGehee thesis, and we change xi1 hat, xi2 hat to xi1 and xi2. Okay, and this change is given just by some rotations, which depends on the point. This phase here is this expression here. We just change coordinates rotating a little bit. And then in these new coordinates, xi1 and xi2, now the flow, the rotating Kepler problem, the flow is given by these two equations here. So it's again like in each complex plane, xi1 and xi2, we see rotations, but now the rotations are constant along the trajectories. Okay? Because h is an integral of motion. So in both factors, it rotates along the trajectory with constant angular velocity. Another thing that is very important from this expression here, first of all, h is a number bigger than 1. So what we see here in both factors it's a positive rotation. It rotates positively. Okay? And h is also a real analytic function. And monotonic. In the following sense, so let me describe the flow here, given by these equations. Again, we have the same. The flow is on the three-sphere with this special radius. Okay. We have this function here, which differs from this factor to this factor. This expression here. And we find directly two special periodic orbits. For instance, we can make xi2 equal to 0, so it remains 0. And then xi1 will be just a circle, given with this precise radius here. So it's a circle and a point here in xi2 and a circle in xi1. And this is called the direct orbit in the rotating Kepler problem. It's a periodic orbit. And we can do the opposite, which is fixing xi1 equal to 0 and taking xi2 equal to the trajectory which rotates in the second factor in a circle with radius square root of 2. It's another periodic orbit of the system, which is the retrograde orbit. There is a meaning of this being direct and being retrograde with respect to the rotating system. So we have these two periodic orbits, like when it moves one, and then the other moves the second factor. And then, so in this three-dimensional space, which is the three-sphere, these two periodic orbits, they form like a Hopf link. In fact, they are like that. Okay, in these coordinates, we don't see it, but in the three-sphere, they form really a Hopf link. They are linked like that. Okay, the direct and the retrograde orbit. And then, for instance, we could like fix the radius of Xi1, and on Xi2, the radius is given by that equation, and the trajectories will rotate with different speed. They might close or not, depend on these factors here. Like if the ratio of those factors are rational or not. And of course, if we fix the radius, like we have a lot of initial conditions which gives different trajectories. In fact, you have a circle of initial conditions, like you fix the point here and you can change the initial point along the circle, fixing both radius. And these trajectories will give rise to an invariant torus for that given pair of radius. It's a pair of torus. And you can, like, deforming the radius in both factors from 0 to square root of 2, and you obtain a family of invariant tori, which goes from the direct, let's say the direct orbit here, to the retrograde orbit. It foliates the complement of these two orbits. Like, and what I was saying about that term H is that this H is constant on each invariant torus. Okay? It has the same value on each invariant torus. And for different invariant torus, it has different values. Okay? So it's like this function, this H is monotone from the direct orbit to which is a degenerate torus, to the retrograde orbit. It's another degenerate orbit. It's monotone. So it's an analytic function which is monotone. So the flow is completely described by this equation in a very simple way. Okay, so now it is possible to present almost explicitly, in fact explicitly, the Annulus-like global surface of section. So we have those two periodic orbits. This is the direct, and this is the retrograde. Just explain this. And in the complement of these two periodic orbits, it's foliated by this one-parameter family of invariant tori. Okay? And the annulus is a function. Will be this function defined on the annulus with values on that three-sphere that I said in the beginning. This three-sphere, I'm calling this a three-sphere, in this, which corresponds to the flow on that component of the energy level, and it has this expression here. So it's very explicit. So it's like in these coordinates here, theta r, we would see like this annulus connecting the direct to the retrograde orbit. And if you realize here, this so the projection, like the projection of the annulus to the first factor is just like the whole disk from the direct orbit. When r equal to 1, it's on the direct orbit, and when r goes to 0, it traverses in the opposite direction the retrograde orbit here. So we have this sign here, which means that when you move theta, let's say positively, in the first factor it moves positively, but in the second factor it moves in the opposite direction. So it's not so difficult to see that this will really be an Annulus-like global surface of section. So the boundary is formed by the Hopf link, direct and retrograde orbit, and the interior is transverse to the flow. Because of this negative term here, the flow always rotates both directions, both complex planes in the positive direction, but the annulus is in this parameterization moves the second factor in the negative direction. So whenever the annulus, the trajectory touches the annulus, it will flow transversely to the annulus. And again, because of this expression, if you take any solution in between in one of those invariant tori, you're going to see it must necessarily hit a point in this annulus. So it's really a global surface of section given explicitly. And moreover, in these coordinates, it's even possible to compute the first return map. The first return map depends on these factors here. So this function h. And in the end, so the first return map, this psi here, it has this very simple form here, which means that, so putting coordinates theta and r on the annulus, then r is preserved because the solutions will just rotate in the first factor, so the r doesn't change. When it hits back the annulus, it has the same r. But in the theta direction, it might rotate, like the map is given by theta plus a function which depends on r, and this function will be monotone and analytic. So you can imagine like an annulus map, like here the lower boundary, the upper boundary of the annulus. These sides are identified, and the first return map preserves the horizontals. And it preserves the horizontals, but it shifts in each horizontal by a different quantity. So this means that in the upper and the lower boundary, they are twisting for some quantities that are given by this function here. It depends on these terms here. So you can explicitly compute the first return map in these coordinates for the rotating Kepler problem. So it's really shifting, and it's twisting the boundary components. And so the construction of Poincaré is the following. So these periodic orbits, the retrograde and direct orbit, they are in general, they are non-degenerate. So if you consider mu greater than 0, then the flow, it's possible to show that it's a smooth perturbation of this rotating Kepler problem. And these orbits in general, they are non-degenerate. So if you perturb the flow a little bit, so they persist. And also the annulus global surface of section, it might modify a little bit, but they persist. It's essentially the construction of Poincaré. That's how, and that it will preserve an area form. That's very important for that theorem. And it will, again, with this small perturbation, have the twist condition. So if you have a theorem for annulus maps, which gives periodic orbits, then you might apply to the three-body problem. That's what Poincaré studies. So you have this annulus map. Even so if you fix the low energy of the rotating Kepler problem, if you perturb a little bit this parameter mu, make it positive but very small, you still have this structure. You have this homeomorphism, the annulus map. You have the twist. So you have infinitely many periodic orbits. So when you perturb, just a picture here that I find very interesting is this picture by Chansinet. Is, let's say, very close to the real situation in the three-body problem. So we have the direct orbit here, the boundary. This is an annulus connecting the direct and the retrograde orbit. So here, this is the other boundary component, the retrograde orbit here. They form a Hopf link. And here we see the annulus connecting them. And this is for the perturbed case. So in the rotating Kepler problem, we would see a lot of invariant tori here, a lot of like closed curves corresponding to this invariant tori. They are homotopic to the boundary. But when you perturb, of course, dynamics gets more complicated, and then you can see some chaotic regions, some elliptic islands, and Chansinet, he also, see this picture here, it corresponds to the original system, how like the orbits here would be almost periodic or almost periodic, and they would look like this picture, like in the original system, where this dot here corresponds to the primary. Okay. So this is the retrograde that we see moving in this. This is the direct orbit that we see moving in the counterclockwise the direction, and the retrograde orbit is moving the clockwise direction. That's the reason of the names. And here we see these other orbits which look periodic, and the projection on the Q plane in the original coordinates, they look like this. These figures here. Okay. So this is what really happens in the three-body problem when you are close to the rotating Kepler problem. Okay, so I will now come back to that statement of the Poincaré-Birkhoff theorem, and try to give an explanation why these periodic points exist. So, but I will consider a simple situation, because the proof, in fact, so let me just recall the statement. You have an annulus map, which preserves area, preserves orientation, the boundary components, all these topological conditions, and it twists the boundary in opposite directions. And you must have these two fixed points. Historically, so Birkhoff proved, but some people did not agree with the proof of the second fixed point. It took a while for people to be convinced that it was really true. You can find some proofs of the second fixed point in the literature that are, say, good proofs. Some are not so good. And Poincaré, in that first paper that I mentioned, he gave a sketch of a proof. He said that maybe he wouldn't have time to finish the proof of that theorem. And so he gave some ideas on how to prove. So Birkhoff proved like 1 year after that paper, that publication of Birkhoff. But much later, I think that in the 80s or the 90s, some people gave a proof based on the ideas of Poincaré, and he was right. That strategy really worked. I think it's a paper by Gollet and Howe. So it's a long history about the proof of this theorem. I cannot give a complete proof of this statement here, but I can give an idea of why this theorem works in a situation which is close to the situation that Poincaré worked. Poincaré, in the circular planar restricted three-body problem, he didn't really need this full statement. He needed something much weaker, and this weaker situation he gave a proof. But he could see this much stronger statement that I put before. So I will consider the following situation, which is more or less close to the situation that Poincaré needed to obtain infinitely many periodic orbits, which is the following. So we have the Annulus map. Let's take coordinates here, x and y here. And so let's take a lift of this Annulus, okay? And we assume that, so this lift we can express with functions capital X and capital Y here, okay? And let's assume that this map is C1 to simplify, okay? Sometimes it's not C1. It's just a homeomorphism which is smooth in the interior of the annulus, but might be only continuous on the boundary. But here I will assume that this map is C1. So these functions here will be C1. Okay, and it preserves the area. So this, and the standard area form here. So this coefficient 1 here. I will not complicate. So the preservation of area is given by this expression here. Okay. And then I will add this hypothesis, which is satisfied in that condition that Poincaré was working, which is the monotonicity condition, which is like the derivative of the second term. Let's say the second term is the vertical term. The strip is like that. The derivative of the second term with respect to little y is positive. So this means that if you take like a vertical segment in the strip, then you look at the image, it's like when you go up this segment, the image also goes up. This is called the monotonicity condition, okay? And then when you have this condition, let's say that the strip has coordinates x and y, then you can combine, or you could take coordinates capital X and capital Y on the strip, but you can combine little x and capital Y as coordinates on the strip. And this is the main trick to produce the fixed points. And again, of course, to produce the fixed points, we assume this twist condition here, which means that the lower boundary component, the points move to the left here. There's inequality here, and the upper boundary, it moves to the right, which is given by this expression here. Okay? So this is the twist condition. It preserves area, and it has the monotonicity condition. If we look at that map that I said here, so this would play the role of the little y, and this would play the role of the capital Y. So it's the identity here. So the derivative is just 1, so it's positive, so it's monotone. It preserves the horizontal, it's monotone, okay? And if you perturb a little bit that map, it's still monotone. So you have a situation very close to the one that Poincaré considered. Okay, so I will give an idea on how to obtain the fixed points when under these assumptions here, with this monotonicity condition. Of course, the general case, you don't have this monotonicity, this argument doesn't work. So So the idea is to replace the problem of finding fixed points with the problem of finding critical points of a real function on the annulus. Okay? So this real function is the generating function of this map here, of this map here. Okay, so what we do? So to prove the existence of this very special real function, we consider this one form. So as I said before, the strip, let's say the strip, we can take coordinates little x and capital Y. Now, because of the monotonicity condition, we can replace little y with capital Y, or if you wish, capital X with little x. Combine these coordinates to produce. It's a new system of coordinates on the strip, and we fix that system of coordinates here. So here is a one form on these coordinates here. Why? Because little x here. Capital X depends on little x and little y, but little y, again, you can express as a function of this guy. Here we have capital Y, okay, capital Y, and again, little y can be expressed as a function of these guys. So this one form here is, that we see, is a one form in these coordinates here, okay? And this one form, now it's very simple, in fact. You can take the derivative, and it simplifies a lot. It just remains the terms, the area forms in the, let's say, in the domain and in the target, and one minus the other. But because the map preserves area, now the derivative of this one form here is zero. So this one form is closed. And because you are on a simply connected space, so this one form here has primitive, so it's exact. So you can express this one form as the derivative of a C2 function, because so this one form is only C1, because of this term here is assumed to be C1. So this function here will be C2. Its derivative is C1. So here, what now okay. So now we see by this equation here, comparing this equation here with this one, this term should be the derivative of S with respect to Y, capital Y. And this term here should be the derivative of S with respect to little x. So we obtain these equations here. And these equations are directly, you can see from here, that if you have a critical point of this function, which is called the generating function of that map, if it's a critical point, so it gives you, in those coordinates, a fixed point of the map. So all we have to do is to show that because until this point here, we haven't used the twist condition. And the twist condition will be the final ingredient to show that this function here has a critical point. So we have to find this critical point. So how do we do it? It's in fact very simple, because let's see. First of all, it's so this is the derivative of y, derivative of x, and this expression on the left side, little x minus capital X is a function on the strip, which is periodic in the x direction. It's one periodic in the x direction. And this and this is one periodic because x is a lift of the Annulus map. So this is a function which is periodic on the strip, which is with period 1 in the x direction, little x direction. And here also, because it's a lift of the Annulus map, it's a function which is one periodic. So these two functions here that we see, they are periodic in the x direction with period 1. So the derivative of s is periodic, but s might not be periodic, only the derivatives. So we have to show that, in fact, this function is periodic. Not only the derivatives, but the function itself is periodic. And to do that, to show this, that this guy, the function s is periodic, we integrate in the x direction, in the little x direction, along like a horizontal line, okay? In that interval, let's say, with length 1, and we have to show that the integral of this term here is equal to 0, so it doesn't change. So, but this is very simple because this map preserves the boundary components. So capital Y and little y coincide in each boundary component. So this guy is equal to 0 in the boundary component. So when you integrate this function in the x direction, you integrate 0, so it's 0. So this function does not accumulate something, even if the derivatives are periodic. The function itself will be periodic in this direction, which means that this function s, let me show this. This means that the function s descends to a function on the annulus, okay? Because it's periodic, one periodic. It descends to a function on the annulus. And now we are in a compact space. We can argue easier to obtain the critical point. And this is done as follows. Because of the twist condition, so we see here that, let's consider the lower boundary. So here is 0 because y is preserved. So it's, this guy here is 0. This means that the derivative of s with respect to x is equal to 0. But because of the twist condition here, the points on the lower boundary, they move to the left. Okay, so this guy here is positive, okay, on the lower boundary. And this means, by this identity, that the derivative of s in the y direction is positive, which means in the end that the gradient along the lower boundary points perpendicularly towards the interior of the annulus. And if you look at the upper boundary and you do the same reasoning, then you show that the gradient of this generating function on the upper boundary component is pointing to the interior of the annulus. So you have this smooth function, which must be constant along the boundary. Okay. It's constant because of derivative with respect to x is 0 because it preserves the boundary. So this is 0. So it's constant, and the gradient points to the interior of the annulus. So if you have a function on the annulus with this property, then the maximum of this function must be in the interior, must be a critical point. And so the maximum will give a fixed point of the map. So that's how you obtain one critical point in the interior. So it corresponds to a fixed point of the original map. And of course, the second is much more complicated than in this situation. I will not discuss its existence, but it's much more tricky. You have to use a minimax argument to show that if there is, to get a contradiction, in fact, if you assume that there is no other critical point, then you use a minimax procedure to obtain a saddle point of this function. But this is much more tricky. So I think I will stop here Thank you very much.